Hello, welcome to Stat 441 at Virginia Commonwealth University. This lecture will discuss the normal probability distribution. And this is part of chapter 5, which is the continuous random variable. Okay, so let's first look at the density function of a normal random variable. So we have defined this variable y, which follows the normal distribution. So it's basically the bell-shaped curve that we have seen earlier. And this is what the probability distribution looks like. F of y is given by this function, and this function includes mu, which is the mean of the distribution, and sigma squared, which is the variance of the distribution. Okay, so it's a complex distribution. The variable y can take the values from negative infinity to infinity. Okay, now this normal distribution, as we understand, it can take infinite numbers on the number line, and it can vary for all the combinations of mu and sigma. So basically, there is an infinite number of normal density functions, one for each combination of mu and sigma. So there are infinite combinations of mu and sigma possible. Therefore, there are infinite number of normal density functions. Okay. So a closed form expression cannot be obtained for the integral of the normal density function. So we will not try to integrate the f of x for the normal distribution. Instead, what we will do is we will work with the area under the normal curve, and we will try to calculate the probabilities using some approximation procedures and the following theorem. Okay. Now, this theorem, we actually have seen this before when we calculated the z-score of a value of y. So what we will do is we will again use this transformation. So if our variable is y, if the value of the variable is y, then if we do y minus mu divided by sigma, that is, we subtract the mean and divide by the standard deviation, then our variable y is basically transformed to a standard normal variable, which we will use the letter z. And this standard normal variable is just another normal distribution, but with a mean of 0 and variance of 1. Okay, so basically what we are doing is any given normal distribution, we will transform it to a standard normal distribution with the mean of 0 and variance of 1. The area under the curve for the normal distribution with mu and sigma is 1, and the area under the curve is for the standard normal distribution is also 1. So we will use this transformation, and then we will approximate the area under the curve for the standard normal variable to calculate the probabilities. So there is a table which is given in the book. It's table 5 of Appendix B that comes up in the next slide. And we will use that table. So if you recall from chapter 2, the z-score of a value y for the normal distribution is the distance from the mean in terms of the standard deviation. Okay, so here also when we calculate the value z for a given value y, then it is basically the distance from the mean in terms of the standard deviation. And this is what the standard normal table looks like. So this first column here is the z values, and as you can see, it starts at 0 and then 0.1, 0.2, it goes up to 3.0. On the top is the second decimal place of that z value. And within this table is the area. Now, the area that is given here is this strip here. So basically, if I say the z value is 1.0, then this is the area under this curve. So from 0 to 1.0 here. Okay. Now this table can be used to calculate the probabilities. So a few things that you need to remember about this table is the standard normal distribution is symmetric. So for the negative z and the positive z value, the area is the same. So if this side is 1.2, and the area will be given here. So 1.2, this is 0.02, the second decimal place. So the area for 1.2 is this value here. Okay. And then if the z was negative 1.2, it will be the same value because of it being symmetric. Okay. So this is how this table will work. First, we will start with our normal distribution. We will change the y variable to a z variable. That will give us the z value. And then we will use this table. And this table basically gives us this area. Okay, so here is an example. If z value is 1.33, so from 0 to 1.33, this is the area. Okay, and depending on what probability we are interested in, we can figure out the total probability. So 0 is in the middle, which corresponds to the value of the mean. Area below 0 is 0.5, area above 0 is 0.5. And then depending on what area we need, probability of less than, then we look at the area to the left. If we need the probability of greater than, we look at area to the right of that given z value. If we need in between probability, then we subtract the bigger piece from the smaller piece. There will be three types of problems for this: finding the less than probability, greater than probability, and in between probability. So the best way would be to just draw the normal distribution and then find out the z value, okay, and then try to draw what area we are interested in. And then we can use the table 5 to find the probability. Okay, so here's an example. Let's say we want to find the area under the normal curve between 0 and 1.33 from the table. So this is the diagram here. So between 0 and 1.33, so we need this area from the table. Okay, so this is how we will read it. First, we will move down to the left column and find z equals 1.3. Then we move on the top to find 0.03. Like I said, this is the second decimal place. So this will be 1.33. Okay, the entry at the intersection will be the area that we are looking for between 0 and 1.3. It's 0.4082. So let's look at where it is. So this is 1.3, and this is where the third decimal place is. Okay, so the intersection of these two will give us this area between 0 and 1.33. Okay, another property that we can use is the fact that the normal curve is symmetric around the mean. So area to the left of the mean is equal to the corresponding area to the right of the mean. So if we have, let's say, 0 in the middle, 0.68 on the right, and then negative 0.68 to the left of 0. So from the table for 0.68, we can find the area is 0.2517. So from 0 to negative 6.8 is the same area. It's again negative 0.2517. Okay, so here is how we can find it. For 0.68, this is what we will do. First, we will find 0.6, and the second decimal place is 8. So this is where the number is. Okay, so this is for from 0 to 0.68. So the same area is from 0 to negative 0.68. Okay, let's look at an example and then find the probabilities using the table. So here's what we are given. We know that y is normally distributed, not a random variable. The mean is 10 and the standard deviation is 2.1. First, we need to find the probability that y is greater than equal to 1. And then we need to find the probability that y is between 7.6 and 12.2. Okay, so let's first try this, finding the probability of y greater than equal to 1. So the first step would be to convert this variable y to its corresponding z value. So z value corresponding to y equals 11 will be 11 minus the mean, which is 10, divided by standard deviation, which is 2.1. So the corresponding z value is 0.48. So we can basically, this is equivalent. Probability of y greater than equal to 11 is the same as the probability of z greater than equal 0.48. And then we can use this area under the normal curve, which would be corresponding to this shaded area. Okay, so we have 0 in the middle. Then we can use the three standard deviation marks. So 1 standard deviation, 2 standard deviation, and 3 standard deviation. The z corresponding to 11 is 0.48 right here. We need the probability of z greater than 0.48. So it's the area on the right hand side, greater than. Okay. Now, in terms of how the table works, if we look up 0.48 from the table, it will give us this area between 0 and 0.48. It doesn't give us the area on the right directly, it just gives us this strip. So how will we find the area on the right hand side? So this is what we know. We know that total area to the right of 0 is 0.5. If we can find this value, this area between 0 and 0.48 from the table, so 0.5 minus this area should give us the gray area. Okay, so that's what we will do exactly. So from the table, we will look up the area corresponding to 0.48. So 0.4 is here, and then 8 is here, which corresponds to 0.1844. Okay, then we know that the area to the right of 0, the middle 0, is 0.5. So going back to the figure really quick. So this is what we just found out from the table. Total area is 0.5. So 0.5 minus 0.1844 will give us 0.3156 as the probability of y greater than equal to 11. So this is the process that we will follow. Convert the y variable to the z, find the corresponding area from the table, and then you don't have to convert it back. That's the same area that would apply to the y variable. Let's look at another example. This time we need to find the probability between 7.6 and 12.2. Okay, so again, what we will do is first convert both y1 and y2 to z1 and z2. So 7.6 minus the mean, which is 10, and sigma, which is 2.1. These two values are given to us, 10 and 2.1. So the corresponding z1 is negative 1.14, so which is here to the left of 0. Z2 is again 12.2 minus 10 divided by 2.1, which is 1.05, so which is right here. So the probability will be this total area, okay, between negative 1.14 and 1.05. Now think about this. The table gives us this piece. If we look up 1.05, okay, this piece will be A2. And for this side, to find this area, the table doesn't have the negative values, but we know if we look up 1.14 from the table, it should be the same area because it's symmetric. So we have to find two probabilities from the table, one corresponding to 1.05, which is this, and the other corresponding to 1.14, which would be the same as A1. A1 plus A2, these two combined, will be our probability that y is between 7.6 and 12.2. So this will be much easier then trying to integrate that function, we can use the table. Okay, so from the table, we will look up the probabilities corresponding to 1.14, which would give us A1, 1.05, which will give us A2. So A1 corresponds to 0.3729, A2 corresponds to 0.3531. And when we add them up, we get 0.7260. So the probability of y between 7.6 and 12.2 is 0.7260. Thanks for watching. I will be posting more examples on how to use the normal distribution table and then calculate probability.